We're going to talk about a lot of gas laws, and these are mathematical relationships between the quantities or the basic properties of a gas. So when we talk about a gas, there are four parameters that we talk about. The pressure of the gas, and we use capital P for that. The volume, capital V. The temperature of the gas, capital T. And the amount of gas. And the amount of gas is most conveniently done in moles rather than in grams. These properties are interrelated. When one changes, it affects the others. And the simple gas laws just describe relationships between pairs of these properties. So let's look at what's called Boyle's law. So this was demonstrated by Robert Boyle back in the 1600s, right? Using a J tube. It's just a U tube that was short on one side. I am not going to test you on the name of this law, on the name of the scientist, or when he lived, but I think it's good to just hear about it. Okay, so I'm going to talk about these guys, but I'm not going to test you on that. So he looked at the relationship between the volume of a gas and the pressure of a gas. So he took this J-shaped tube and he capped one end. He put a stopper in here, and then he's got mercury in here. So there's, it looks like nothing, but there's air. There's a gas in there. And we can tell from the pressure, we can tell because the levels are not the same, that the pressure inside there is larger than the pressure outside, because it's pushing the mercury down. So we can measure the difference in pressure with a ruler. And then he put more mercury into the tube, and that is heavier and is going, trying to come down, and so it forces this side up. And we see that the size of the gas, the volume of the gas got smaller. We can still measure the difference in pressure between inside and outside by measuring the difference between the level here and the level there. The difference in levels, the pressure has gone up, the volume has gone down. Do you see it? So when the pressure of a gas is higher, its volume becomes smaller. It's an inverse relationship. When one goes up, the other goes down. So he did things like measuring the volume of a gas and its pressure, and then you could make a graph like this. You can graph the volume of a gas versus the pressure, and we see this relationship. And that's not a nice straight line, it's a curve, right? Curves are harder to make equations out of. So he found that the volume of a gas is proportional to 1 over the pressure. And this is assuming that the temperature and the amount of gas are constant. So when you graph the volume versus the pressure, you get a curve, but if you graph the volume versus the reciprocal of the pressure, you get a straight line. I'll come back to this slide, but let's look at the graph. So here's volume versus pressure curve. If we graph volume versus 1 over the pressure, we get this nice straight line. So we can, when P increases, V decreases. That tells us that the pressure times the volume is equal to a constant for that particular gas sample. If you increase this one, that one has to go down. And so the way we typically express Boyle's law is this way: P1V1 equals P2V2. It looks a lot like the dilution equation, but it's pressure. Yep. This will be on the test, yes. Yeah, you need to memorize the simple gas laws. And I'll also show you how you can derive them very easily from the ideal gas law, but that's coming later. So molecular interpretation, what's going on with Boyle's law? Here we've got a volume of gas that's 1 liter and its pressure is 1 atmosphere. It's got a movable lid, and right now there's a 1 kilogram weight sitting on it. If we double the mass of that weight, it's going to push the lid down. It's going to make the volume smaller. Now the volume's half a liter. We cut the volume in half, and the result is that the pressure doubles. So by whatever factor one decreases, the other increases by the same factor. Because now we have the particles are going to be colliding more frequently with the walls because they're stuck in a smaller space. And that's why the pressure goes up. The gas laws are important in scuba diving because as you go below the surface of the water, water is much more dense than air, and so it puts a lot more pressure on you than the air does. So for every 10 meters, that you go below the surface of the air, for every 10 meters that you go below the surface of the water, the pressure you experience from the weight of the water around you increases by an atmosphere. So this diver is 20 meters down. So the pressure has gone from 1 atmosphere at the surface, 2 atmospheres at 10 meters, 3 atmospheres at 20 meters. 3 times the pressure is a significant difference. So if you're down there, 20 meters down, and you're breathing through with a scuba tank, and you take a breath, the air in your lungs is at 3 atmospheres of pressure. If you hold your breath and go up to the surface very quickly, now the pressure outside of your lungs is 1 atmosphere. Pressure inside is 3 atmospheres. Is that a good thing? No. Your lungs could explode, right? Very, very bad. So the lesson there is always exhale when rising if you're scuba diving. There's a very good reason that they make you take all these lessons and get certified before they let you go scuba diving. Because there are a lot of things that if you do one thing wrong, it could kill you. Personally, I don't understand why anyone would want to go down there, but, there it is. So,
then I watched a movie called, I think it's called 47 Meters Down. It was like this lady. Oh, you watch it too?
No, I don't watch movies like that.
Yeah, I
They're creepy.
If my dad made me watch it, I ain't gonna.
Yeah. It's just, I don't know. It's just not interesting. No. Okay, so this problem, well, we're just going to do it. So here we get a problem. A snorkeler takes a syringe filled with 16 milliliters of air from the surface where the pressure is 1 atmosphere to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? If the pressure increases by 1 atmosphere for every additional 10 meters, of depth, how deep is the snorkeler? Okay, this is what I think of as a challenging Chem 1A problem. I'm not sure why the author chose to give this as the first example of a gas law calculation. But you could see something like this on a test, and so it's probably not exactly obvious what you need to do. So we need some critical thinking and some problem-solving skills. It can help to draw a picture. Your pictures don't have to be beautiful. You don't have to show them to anyone. But I'm going to draw some pictures here. So we've got some water, right? So here's the surface of the water. And it says that the snorkeler takes a syringe with air from the surface. So let's draw a syringe up here. I'll just leave the needle off. And the syringe up here, and it tells us what the volume of the air in there is. It's 16 milliliters. And he takes that syringe, or she, and brings it down here. Oh, we need the plunger. And it says that the volume of the air down here is 7.5 milliliters. So I'm going to make that smaller. So that's 7.5 milliliters. So it's like the plunger has been pushed in, right? It was longer here. Why did the gas get smaller? Because the pressure changed. As you go down under the water, you get more and more pressure. If you've gone down to the bottom of a swimming pool in the deep end, you might feel in your ears there's pressure, right? It's the water pushing on you. So we have a volume change, and what do we know about the pressure at the surface of the water? It's 1 atmosphere. So up here, the pressure is 1 atmosphere. And down here, do we know what the pressure is exactly? No, in fact, that's the question they're asking. What is the pressure at this depth? So that pressure equals, we don't know. That's messed up. We don't know. This is a volume, and this is a volume. So I've got 2 volumes and 2 pressures. I know 3 of these quantities, and I'm looking for 1. So what we want is an equation that's going to relate pressures and volumes. And that's Boyle's law. P1 V1 equals P2 V2. It doesn't matter which one you call 1 and which one you call 2, but it's important that this P and this V have the same number, right? Because these go together, and these go together down here. So I'm just going to call the ones at the top 1. This is P1, and this is V1. And then down here, this is V2, and that's P2. Everybody okay with that? So what I want to find is P2. I need to rearrange this equation. There is a lot of rearranging simple equations. And so if you struggle with that, please get some help either from me or from somebody else, because it's just that you forgot how to do it, and we can bring that back. You're going to need it. So here I want to rearrange this equation before I stick the numbers in. And I'm trying to find P2. So I want to get P2 by itself. So I need to move anything that's with P2 to the other side. And I'm going to do that by dividing both sides by V2. If I do the same thing to both sides of an equation, it's still equal. The reason I chose to divide by V2 is because V2 divided by V2 is 1, and it cancels out. Okay? So P2 then is equal to P1 times V1 divided by V2. You can imagine it's really easy to get your subscripts mixed up, so be real careful with that. So I want to put in pressure 1, it's 1 atmosphere, times volume 1, 16 milliliters, divided by volume 2, 7.5 milliliters. And if I look at the units, I see that the milliliters cancel out, and I'm left with atmospheres. So I get out my calculator, and it's 16 divided by 7.5. And it's telling me 2.13333. Well, I should really only have 2 significant figures. So I'm going to say the pressure there is 2.1 atmospheres. Any questions? The other question involves a little more thinking. It's reminding us that the pressure increases by 1 atmosphere for each 10 meters of depth. How deep is the snorkeler? So 1 atmosphere is equal to 10 meters of depth. We can use that as a conversion factor, but that's an increase in pressure So from the top to the bottom, how much did the pressure increase? Not what is the pressure, but how much did it increase? 1.1, right? Down here, 2.1. Up here it's 1. So the difference in pressure is 2.1 minus 1, or 1.1 atmospheres. So the pressure increased 1.1 atmospheres, and then we can use that relationship, 1 atmosphere per 10 meters. 10 meters for every 1 atmosphere increase. So that tells us the diver is 11 meters below the surface of the water. I got 1.1 because what I'm looking at is the increase in pressure. At the surface, you have 1 atmosphere of pressure. So the depth is related to the increase in pressure. So I have to take the pressure down here where I am and subtract the pressure where I started. Any questions? The important part of this is the green. The purple stuff is like extra. Let's talk about Charles, J.A.C. Charles. He lived in the 17 and 1800s. He looked at the relationship between the volume of a gas and its temperature. And he found that the volume of a gas is directly proportional to its absolute temperature. So absolute temperature is the Kelvin scale. The Kelvin scale, 0 is the lowest theoretically possible temperature. So you can never have negative Kelvin temperatures. You're not going to have 0 either. So Charles' law says that volume is proportional to temperature. The temperature has to be expressed in kelvins. Anytime we're doing gas calculations, the temperature has to be in kelvins. And so Charles' law is often expressed this way: V1 over T1 equals V2 over T2. If you use Celsius or Fahrenheit, you could end up with a 0 temperature, and you can't divide by 0. That would be undefined. So if that helps you to remember, it's not the only reason we have to use Kelvin, but it's an important one. So here we have some Charles' law data. We've got the volume of a gas versus the temperature of the gas, and we're showing 2 different temperature scales here, degrees Celsius and Kelvin. We've got 3 different lines here. These are representing different amounts of gas. For comparing volume and temperature, the pressure and the amount of gas have to stay the same. So here, this is 1 mole of gas at 1 atmosphere. When we graph this, we get a nice line. Half a mole, we get a different line. And 0.25 moles, yet a different line. If we extrapolate, which means we're drawing the line past where we actually have data, we find that all of these lines intersect at a 0 volume at minus 273.15 degrees Celsius. So what this is suggesting is that at that temperature, the volume of a gas would be 0. Is that actually possible? Could a volume be 0? No. But that predicts that, everything lines up with that, and so that's our absolute 0, is minus 273.15 degrees Celsius. So that was made 0 Kelvin. The size of a Kelvin and a degree Celsius are exactly the same. And so like here from 100 to 200, there's a difference of 100 degrees Celsius, there's a difference of 100 Kelvin. All that's different is where 0 is defined. The Celsius scale defines 0 as the freezing point of water. So we could never have negative volumes, and we're going to never have 0. It's absolute temperature, and the minus 273 is absolute 0. You can observe the relationship between volume and temperature using balloons. You could try this at home. Here's a balloon, and if you put it in ice water, it'll shrink. And then if you warm it up, put it in boiling water, it'll expand. Because the volume of a gas is proportional to its temperature. Higher temperature, larger volume. Lower temperature, smaller volume. What happens is, with a higher temperature, temperature is a measure of the average kinetic energy of the particles. Kinetic energy is the energy of motion. So at a higher temperature, gas molecules are moving faster. That means they're going to run into the walls more frequently and with more force. So that would increase the pressure, but we're keeping the pressure constant, and the only way to do that is to allow the gas to expand so its volume becomes larger. This is a picture of a regular balloon in liquid nitrogen, and it just like really shrivels up and gets very, very small. Charles' law is also the reason that hot air balloons work. I remember being puzzled by these as a child because, you have experiences with helium balloons, but those don't work if they have a hole in them. And if you blow a balloon up with air, it doesn't float. And yet here we have a balloon that has a giant hole in it, and it's full of air, and yet it can lift people up in the air. What's up with that? Well, it also has this ginormous burner here. And what that does is it heats the air. Because of this big hole, the pressure inside the balloon is going to be the same as the outside. But you heat the air, and it expands, and so a lot of the air leaves the balloon. What does that do to the density of the air? You've got less air in the same volume, the density is lower. The reason a helium balloon floats is that the density of helium is less than the density of air. By heating the air, we can make the density of the air less than the air outside, and the balloon will float. That's how those little, I don't know what they call them, the little paper bag-like things with a candle, how do those fly? I mean, such a crude little device, how does that fly? Because the candle is heating the air. It's the same idea as a hot air balloon. So here's an example of a Charles law problem. Talk a lot about gases in cylinders with movable pistons, because it's a container where we can change the volume. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 to 155 Celsius, what's its final volume in milliliters? So when we're dealing with gas laws, we're going to have a bunch of numbers, and we need to organize them. So this isn't the only way you can solve these problems, but it's a good way. Let's make a table. Let's just collect the data and make a table. So the first number I come across is 88.2 milliliters. So I'm going to write that down, 88.2 milliliters. And that is the volume, right? We should recognize that milliliter is a unit of volume, but it also says it has a volume of, right? So I'm going to label this row in my table V for volume. And then I go along and I see I have two temperatures here. So I'm going to have another row here. It's going to be temperature. So the temperature goes from 35 to 55. So I've got two temperatures. Which one of those goes with the initial volume of 88? The 35. So this is 35 degrees Celsius. I put it in the same column because those two go together. And then I've got 155 degrees Celsius over here. I'm just going to call the first column 1 and the second column 2. Now, what did I tell you about units on temperatures for gas law problems?
Kelvin.
It's got to be in Kelvin. So I left some space in there. We're going to convert that to Kelvin before we start calculating, because we'll forget later. So 35 degrees Celsius. The relationship is 273.15. Your book's a little sloppy on temperatures here, and I kind of go back and forth. Really, this 0.15, our temperatures here are to the nearest 1 degree. Ideally, we would keep the 0.15, but it does make things a little messy, and this is just an example, doesn't really matter that much. So we can use 273, that's okay most of the time, even on the exam. Yeah, I won't trick you by having 2 answers, multiple choice, where the difference is, did you use 273 or 273.15? That's being very petty. So I'm going to take 35 plus 273, and I get 308. 308 Kelvin. So I'm going to write that in here, 308 Kelvin. I'm going to do the same thing with my 155. 155 plus 273, 428. So now I have a nice little table, and one of my boxes is blank. So in this box, this is row V in column 2. I'm going to call that V2. So I've got 2 volumes, one of them I don't know, and I've got 2 temperatures. I need an equation that's got V1, V2, T1, and T2 in it. And that's Charles' law. P, not P. V1 over T1 is equal to V2 over T2. This equation has fractions in it. My experience is that a lot of students are not on good terms with fractions. So some of you can rearrange this, just looking at it and writing it down. That's awesome. I'm not talking to you right now. The rest of you, let's get rid of the fractions first so that they don't screw us over. So the way you get rid of fractions is cross multiplying. So I'm going to take the top of one side times the bottom of the other side. V1 times T2. And that's going to equal the bottom of this side times the top of that side. That's cross multiplying. At least that's what they called it when I was in school. Actually, let's, the order doesn't matter, but it confuses people. So that's T1 on the bottom times V2 on the top. Get rid of the fractions. Now this is easier to rearrange. I'm trying to solve for V2. So I'm going to divide by T1. Because I want to get rid of the T1. I want to isolate V2 all by itself. And if I do it to one side of the equation, I have to do it to the other side. So I've rearranged my equation. You may or may not need to show this in your work. I end up with V2 equals V1 T2 over T1. And again, copy that carefully, because do you see what I did there? What did I do up here? Yeah, it was supposed to be 1 and I put 2. Dividing by the same thing on both sides. I actually did it right here by accident. You should show the rearranged equation as showing your work, and you should then show it with the values written in and then the answer. So now that I have my equation, I'm going to look in my table. Everything's all organized for me. I'm going to take V1, 88.2 milliliters, include the units, and my temperature, I want T2 up here is 428, and I'm going to divide by T1, 308. And I check my units, the kelvins cancel out, my unit is milliliters. So V2 is equal to 88.2 times 428 divided by 308. Everything's got 3 sig figs. My answer should have 3 sig figs. 122.56. I'm going to call that 123 milliliters. With the simple gas laws, we can ask ourselves, well, does that answer make sense? I took a gas and I heated it up. Do I expect the volume to get bigger or smaller? Bigger. This is bigger than what I started with, so that's encouraging. It doesn't prove anything, but it's encouraging. If this is smaller, then you got something upside down in here. Very easy to do. Any questions? Avogadro, we've heard of that guy before. Amadeo Avogadro looked at the relationship between the volume of a gas and the amount of gas in moles. Avogadro's number is named after this guy. So he found that the volume of a gas was proportional to the number of gas molecules. Not the mass, but the number of particles. So Avogadro's law, the volume is proportional to the amount of gas in moles. We can express this in an equation. V1 over N1 equals V2 over N2. This enables us to count gas molecules. Oh, I'm sorry. Back that up. When we count molecules, we use the unit mole, right? Because anything large enough to see has way too many particles. So we look at the numbers of moles instead of the numbers of particles. They are related. If we have equal volumes of gases, they have the same number of particles. What the gas is doesn't matter. And this is something that's very different about gases than about liquids or solids. So here's some data demonstrating Avogadro's law, the volume of a gas and the moles, the amount of gas. So this makes sense. If you put twice as much gas into a container and you keep the pressure the same, you would expect it to get bigger, right? You blow into a balloon, you put more air in, the balloon gets bigger. That's the relationship here. If we take this and extrapolate to 0, this would predict that 0 moles of gas would occupy 0 volume. Well, of course. So let's do a calculation with Avogadro's law. Chemical reaction occurring in a cylinder equipped with a movable piston, there's that again, produces 0.621 moles of a gaseous product if the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters. What was the volume after the reaction? Assume constant pressure and temperatures and that the initial amount of gas completely reacts. Always read the question all the way through. So we've got numbers here. Let's make a table again. The first number I come to is 0.621 moles. So that is the gas that's produced. If the cylinder contained 0.12 moles before, well, there's another mole amount, so those need to go on the same row. Because they are the same kind of thing, right? This is N moles of gas. And I need to indicate up here whether I'm going to call them 1 or 2. It doesn't matter. So I'm not going to put that in yet. We're going to have another thing down here. So it's telling me about a volume. So this volume, 2.18 liters, I need to be careful which box I put this into. So this is my volume row. Which amount of moles does this volume go with? The 0.120. So this is where we have to read the words as well. So it contained this before the reaction had an initial volume of this. It's asking what's the volume after. So this could be confusing, right?
Yeah, because I was going to ask why was going up there instead of point.
So this is after and this is before, right? It's just that they mentioned the after number first, and so I happened to write it down first. So if it helps, write some words in here to help you keep track. So then if I look at this 2.18, okay, well that goes with before. So that goes in here, 2.18 liters. And then I've got my one empty square rectangle. I could call this 2 and call this 1 if that makes more sense to me. I can call this one 1 and 2. I could use 3 and 4 if I wanted to. It doesn't matter. It's not before and after, initial and final. It's just these two go together and these other two go together. So I'm going to call this column 2 and this column 1 just because it kind of makes more sense that this was the beginning. But it doesn't matter. So then I'm trying to find this V2.
So you use the same formula, you just want to be cross multiply, you just want to use 0.120.
We're going to use a similar, we're going to use Avogadro's law, which looks very similar to Charles' law. So we had volume 1 over N1 is equal to volume 2 over N2. Again, we see fractions, cross multiply, get rid of the fractions. V1 N2 equals N1 V2. What am I trying to find? I'm trying to find V2. So I'm going to divide this side by N1, and I'm going to divide this side by N1, and those are going to cancel out. So V2 equals V1 N2 over N1. I'm going to take my numbers there and plug them into this equation. Volume 1 was 2.18 liters. N2 is 0.621 moles. And N1 in the bottom, 0.120 moles. So you see the mole units cancel out. .18 times 0.621 divided by 0.12. As is typical with book problems, there's 3 sig figs. Write down 2 extras and then round this 11.3, and the unit left is liters. So that's the new volume. Then we should ask ourselves, does that make sense? Here I had this amount of gas, and after the reaction I had more gas. So then I expect the volume to get larger because there's more gas. It got larger, so I probably did it right. Any questions? One more example. Scale model of a blimp rises when it's filled with helium to a volume of 55 cubic decimeters. When 1.1 mole of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant T and P. This sounds like those problems you had in math. You know, Susie's on a train going this many miles an hour at this direction, and you know, all of that stuff. There's a lot of words here, right? Pull the numbers out and then go back and look at the words. So I have a volume of 55 cubic decimeters. Now that's a volume that a unit that we don't use very much, but it's okay. So it rises when it has a volume of 55 cubic decimeters. When 1.1 mole of helium is added to the blimp, the volume is 26.2. So 1.1 and 26.2 go together. So the other volume I'm given is 26.2 cubic decimeters, and that goes with 1.10 moles. So that's N. So it looks like I could solve for, we call this 1 and 2, this would be N1. So let's do that. Need the equation that's got V's and N's in it. V1 over N1 equals V2 over N2. Cross multiply to get rid of the fractions. V1 N2 is equal to N1 V2. N1 by itself, so I'm going to divide by V2. These cancel out. With N1 equals V1 N2 over V2. I'll show you a shortcut. So here we have this equation, and it's two fractions. When I'm rearranging this, here what I did is I cross-multiplied and then I divided and I ended up with this. You can do the same thing in your head. The rule is if you take it from the bottom of one side, you can put it on the top of the other side. If you take it from the top, it goes into the bottom. So I can imagine taking this N1, which is in the denominator, and putting it in the top over here. N2 comes up here, V2 goes down there. If that made sense to you, great. If it didn't, do it this way. So I'm just going to plug my numbers in. V1, 55.0 cubic decimeters. N2 is 1.10 moles. And I've got V2 on the bottom, 26.2 cubic decimeters. Those unfamiliar units of cubic decimeters cancel out and go away. Good riddance, we didn't like looking at you. 55 times 10, no, 1.10, divided by 26.2. 2.3092, and that would be moles. So I found a thing, right? What's the question asking for? It's asking for a mass of helium. How many more grams of helium must be added to make it rise? So here's another situation where we might want to draw a picture. So there's a big blimp, kind of looks like a weird fish. There's the blimp floating, and when it's floating, it has a volume of 55 cubic decimeters. What we're starting with is kind of a scrunched up blimp. It's partially full. And we're told that the volume of that was 26.2 cubic decimeters. And we were told how much helium was in it, 1.10 moles of helium. So we're taking this partially inflated blimp, and we need to get the volume of it up to 55 cubic decimeters by adding more helium. That makes sense, right? We're filling it up so it's going to float. What is this that we calculated? That's the amount, the moles of helium present in the blimp when it's floating at this volume, right? So what we found was up here, N equals 2.3092 moles of helium. Down here, we've got 1.1 mole. It's asking how many more grams must be added. This isn't our answer. We need to find out how much to add. Well, we've got an initial number of moles and a final number of moles. If we subtract, we could get the number of moles we need to add, right? So we want 2.3092 moles. We have 1.10 moles. And so that is 1.2092 moles that we need to add. How do I turn that into grams? Molar mass. 1.2092. I'm just carrying those 2 extra digits because I'm not done with my calculation here. Moles of helium, and then I want grams of helium on top and moles on the bottom. And I look at my periodic table, 4.003. It's the mass of 1 mole. So 1.2092 times 4.003 equals 4.8404 4.84 grams. Did I do that wrong? Nope, I stand by it.